In this video, we're going to look at the central limit theorem. So if we look at those, the question that we kind of left off with in the last video was, we know how to figure out what value the distribution of a population being normal. And we looked at the 68, 95, 99.7% rule for the tolerance of people with this odor in wine. And we asked the question, well, what would we expect to be the mean of a sample of 25 adults? So if we kept pulling 25 adults, what would we expect? So that's what we're going to look at here. We're going to talk about the mean of a sample of n adults. And n is going to change from problem to problem, from example to example, but within each problem, n has to be consistent. You can't draw a sample of 25 and then draw a sample of 35 and compare them in any way. So your entire sample of means has to be from the same size n. So if we take n subjects from a population and find a sample mean for that sample, and then we take another 10 and we find the sample mean, and we keep doing this over and over and over, we could make a histogram or a stem plot of the values of those means that we got every single time we took a sample of 10. And then we can look at it for the shape, the center, and the spread of that data. So back to the case of the wine smelling bad. If we say we did 1,000 repetitions where we took 10 people and we found the mean of their thresholds, and then we took another 10, we found the mean of theirs. We did that 1,000 times and found the means on each of them. What would the histogram look like? Well, here's what the histogram looked like. It's pretty darn close to looking normal. Okay? And if we look at this, we can fit a really nice curve to it. And look where the mean of our curve is. It's at 25, which is the same thing as the population mean. So let's hold on that thought, okay? To talk about the means and the standard deviations of these distributions of sample means. So if we take numerous samples of the same size n, the population has a mean mu and a standard deviation of sigma. The mean of the sampling distribution of x bar, when we take all those samples over and over and over, is going to be mu. So it's going to center itself at the true population mean, which should make some sense because we talked about in the law of large numbers how the bigger our population gets, we converge on that mean. Well, the bigger our sampling of samples of a certain size is, the closer we're getting to that true mean also. And the standard deviation of this distribution of sample means is sigma over the square root of n. So we're making our sigma smaller. We're actually taking out a lot of the variability by taking means instead of individuals. When we put individuals together, we take out variability. So our standard deviation is smaller. It's divided by the square root of n. Now, since the mean of the sampling distribution of x bar is mu, that tells us that x bar is an unbiased estimator of mu. That's what an unbiased estimator is. And again, individual observations have a standard deviation of sigma, but the sample means have a standard deviation of sigma over the square root of n because averages are less variable. And we know from doing this over and over and over that they are less variable by a factor of the square root of n. So if individual observations have a normal distribution with mu and sigma as their mean and standard deviation, then the sample mean of n independent observations, so whether you do 10 at a time or 25 at a time, or any number at a time, if you take the distribution of the sample means from doing that, you're going to get a normal distribution with a mean of mu and a standard deviation of sigma over the square root of n. So if the population is normal, so is the distribution of sample means. So the mean threshold of all adults is 25. Standard deviation is 7. And the threshold values follow a normal curve. And it's this orange curve, this shorter and squatter one. Okay? The sample means is the taller one because it's less spread out. Its standard deviation is smaller. But they're both normal. So this is the real kicker, and this is what is the meat of the central limit theorem. You can take a sample size n from any population with a mean mu and a standard deviation sigma. Doesn't have to be normal. Any population this can be done with. If n is large, then the sampling distribution will be approximately normal. So no matter what distribution the population follows, the sample mean will follow a normal distribution if the sample size is large. And the normal distribution that it follows is mean of mu, standard deviation of sigma over the square root of n. Again, from any population, it need not be normal if n is sufficiently large. So, how large does n have to be? Well, it depends a little bit on how far the population is from normal. If it's really, really skewed, you're going to need a larger sample size. But a sample size of 25 or 30 is typically large enough for any population distribution we encounter in practice. And if the population is normal itself, any sample size will work. So we usually use 25 to 30. 30 is kind of one of those magic numbers in statistics. We use it a lot as kind of the threshold number for things. 30 is going to work in almost any population you will encounter. So this is kind of interesting. A sample size and distribution of x bar. So this is the distribution that we're starting with. N equals 1 means you've only drawn 1. So this is the A is the individual, the population distribution for the individual populations, okay? That is not normal. There's no curve to it. If we take a sample size of 2 and do the sample means, already we start to form a curve. At 10, we have something looking very normal with just a slight skew to the right. And at n equals 25, well, darn, that looks normal to me. So we started out with something that was extremely not normal looking. And just by taking samples of 25 over and over and over, our sample means distribution looks almost completely normal.